Okay, first of all, on page 1 of differentiation, I'd like to talk to you about how the power rule appears in the formula booklet. It looks like this. You may think, oh my gosh, what does this mean? It's the same thing as what we learned in the investigation. If you have, for example, x to the 5th power and you take the derivative, you're going to put the 5 down here first. Then you're going to write the x in the same position, and then you're going to subtract 1 from the 5. So it's going to equal to 5x to the 4th. And this is called the derivative function. You could annotate the derivative function using y dash or f dash of x if the original function was f of x, or dy dx. I think that's all I can think of for now. As far as the instructions telling you to find the derivative function, there are several. Find dy dx, that corresponds to this, right? Find f dash of x, that corresponds to this. Find y dash, that corresponds to this. There's also verbs like differentiate. It turns out that the verb form of derivative is not derivate, it's differentiate. And then there's also the full differentiate the following with respect to x. Some people get confused by the fact that it says the following with respect to x. What they mean there is that the variable that appears here will be x. Okay? Notice here in dy dx that the x also appears on the bottom. That's kind of the same thing. When you have dx on the bottom, it means with respect to x. Now, sometimes we'll take the derivative with respect to some other variable, like instead of x to the n, you're going to have something else to the n. But there's only going to be one variable, okay? So you're not going to be confused about which variable to take the derivative to. Okay, there might be a constant k or something like that, but variable, there's only going to be one. Okay, so we'll talk about those more confusing problems later, but they're few and far between. Okay, so what does the formula booklet notation mean? Do you see how the exponent is called n? So do you see how they moved the exponent down to the front, just like we moved the 5 to the front? And then do you notice how they subtracted 1 from the exponent? So that's all they're saying. They're just giving it to you in symbolic form because this is a rule which applies to any n value. Okay? All right. Let's do a few problems. Okay, so we're going to find the derivative of each of the following functions with respect to x. Okay, so we're just going to find y dash or whatever. These other two instructions here, find the gradient of the tangent at the point where x equals 1, write down the range of values of x for which the function is increasing. We'll come back to that later, okay? All right, remember that we have that derivative rule called the power rule, where if you have like x to the 5th, then you just bring the 5 down here, and then you reduce the 5 by 1, and you get 4 in the exponent, okay? So that's the key rule. Most of the time you're going to be using that. There's two special cases, which I think we see so often that we're just going to end up memorizing it, and I'll justify this for you later. But basically, if you ever have a function which is just a number, y equals 6, that's a horizontal line, right? Whenever you have a horizontal line, the slope is 0, right? And remember, the derivative is the slope. So the derivative of a horizontal line is y dash equals 0, okay? The slope is 0, all right? What about if you have 4x, something like that? Remember that this is in the form of a diagonal line, and the 4 is the slope, right? Whatever's multiplied times x is the slope. So in this case, the derivative of 4x would just be 4, because 4 is the slope. Remember, y equals mx plus c? Well, 4 is m. Okay, so these two rules are rules that you're gonna use a lot, and later I can show you how you can use the power rule to do that. But until you're used to the power rule, that doesn't really help you anyway. Okay, so let's get used to the power rule during this page. Although there's these two special cases, which is if you have y equals 6. It's a horizontal line, slope of 0. Y equals 4x, that's a diagonal line. The slope is the multiplier of x, which is the slope. Okay? All right, next one. Ooh, this one here, it has two things added together, two things subtracted. So what you're going to do is you're going to take the derivative of each one separately, and then you're going to subtract the derivatives, okay? So remember that if you ever have a coefficient already there, you just leave it, okay? And then you're going to do the power rule on x squared. So remember, you're going to bring the 2 down, and then you write x, and then it'll be 2 minus 1, right? What about negative 3x? Negative 3x, that's in this form. The negative 3 is the slope. So we just put negative 3. Okay? Now let's simplify this. 5 times 2 is 10x, and 2 minus 1 is the first, minus 3. So that is our derivative. Oops, let me... Okay, that's our derivative. All right. Let's go to this next slightly more difficult one. 3x to the fourth plus 7x minus 3. Now we're going to break this up into 3 parts, and then we're going to take each derivative separately. So 3x to the fourth, we'd write down the 3, just leave it there, and then we're going to bring the 4 down, and then we're going to subtract 1 from the 4. So 4 minus 1 is 3. That's it, okay? What about 7x? Remember, 7x is, like in this form, 7x. So the derivative of 7x is 7. The derivative of minus negative 3, that's just a horizontal line, right? Horizontal line. So the derivative is 0. So there's our derivative. There's our derivative. Now we're just going to simplify everything. So 3 times 4 is 12, x cubed, plus 7. And we don't need to write plus 0 because plus 0 is invisible. Okay? So there is our derivative for part E. What about part F? Part F, I'm going to first do 5x to the fourth. So we just leave 5 there. And then we bring the 4 down. And then we subtract 1 from the 4, we get 3. What about the next one? Negative 3x squared. So the negative 3 just stays there. I bring the 2 down, and then I subtract 1 from the 2, which would be 1. Plus 2x. Plus 2x, remember, that's in this form here. So the derivative is just plus 2. I just remove the x. What about negative 6? Y equals negative 6. That's in this form here. It's just a horizontal line. So it's plus 0. Now we're just going to simplify. 5 times 4 is 20. X cubed. 3 times 2 is 6. Minus 6x plus 2. That's it. Okay? All right, G. This is slightly challenging, isn't it? Because we have this x in the denominator. Think back to the exponentials chapter. When you have x in the denominator, that's equal to x to the negative 1. Okay? So if we rewrite this function, let's rewrite this function with x to the negative 1 instead of x. Now it looks like the power rule form. I can do power rule on it now because I have x to a power. So let's take the derivative of this. Actually, they used y, so I'm going to put y dashed. The derivative of this is going to be 2, and then I bring the 2 down, this power, and then I'm going to reduce 2 by 1. So 2 times 2, x to the 1. And now I'm going to put the negative 3. I'm just going to leave the negative 3 here. Then I'm going to bring down my power. This is a little bit confusing because it's a negative power. So I'm going to bring down the power. Make sure you put parentheses around it because it's multiplying. And then I put the x here. And then the negative 1 is reduced by 1. Negative 1 minus 1 is negative 2. So it's negative 2. Now I'm just going to simplify everything. So 2 times 2 is 4. X to the 1 is just x. Negative 3 times negative 1 is positive 3. X to the negative 2. And I'm done. Okay, that's my derivative. This one is also confusing because look, I had to first rewrite the function before I took the derivative. And sometimes I do this. I rewrite the function, and after I rewrite the function, I'm like, okay, I'm done, and I don't ever take the derivative. But you need to take the derivative too, right? Okay, let's go to the next one. Oh, here, look at this. 6 over x cubed. So this is another one where we're going to have to rewrite the function first because we have an x cubed in the denominator. Let's rewrite that just like we did here. If you have x cubed in the denominator, that's the same thing as x to the negative 3 in the numerator. And then I just rewrite everything the same way. Now I'm going to take the derivative. The derivative of 6x to the negative 3 is 6 times negative 3. I bring the negative 3 down. And then I reduce negative 3 by 1. A lot of people sometimes say, oh, reduce negative 3 by 1, that's negative 2. No, it's a negative number. When you subtract 1, it becomes even more negative. So it's going to be negative 3 minus 1, which would be negative 4. What about 4x? 4x, remember, is like the slope of a line. The slope of a line is the multiplier out front. It's just 4. And then y equals negative 3. That's just a horizontal line, right? Horizontal line. Horizontal line has a slope of 0, so plus 0. Let's simplify. 6 times negative 3 is negative 18. X to the negative 4th plus 4. And you don't need to do anything with the 0. Okay? All right, last one. We haven't done anything in this form. The only thing we know how to do is a bunch of stuff added together, right? If we have these added together, we know how to take the derivative. We just take the derivative of each one separately, and we add the result together. But this is multiplied together. So you need to change this into a form that is a bunch of stuff added together. Do you remember FOIL? So when we do FOIL, what we do is we're going to multiply the first 2, the second 2, and the inside ones and the outside ones. Okay? So first we're going to do this one. So it'd be 2x. Let me erase everything and use color codes. So first I'm going to do 2x times 3x. And all I'm doing is rewriting so far. I'm not even taking the derivative yet. Then I'm going to do negative 1 times 4. And I add those together. Then I'm going to do the outsides. 2x times 4. Then I'm going to do the insides. Negative 1 times 3x. Okay? Then I'm just going to simplify. 2x times 3x would be 6x squared. All I'm doing is rewriting. This is still just equal to y equals, okay? 6x squared. Blue one. Negative 1 times 4 is negative 4. Green one. 2x times 4 is 8x. And last of all, negative 1 times 3x is negative 3x. Okay, pretty much done. I could combine these two. 8x minus 3x is 5x. Okay, so now I'm going to rewrite it. 6x squared minus 4 plus 5x. I still have not taken the derivative, but I worked so much I might forget to take the derivative. Okay, so let's take the derivative. What's the derivative of 6x squared? I write down the 6, just leave it there. I bring the 2 down, and then the 2, I subtract 1, and I'm left with x to the first. Okay, what's the derivative of negative 4? The derivative of just a plain old number is 0. What's the derivative of plus 5x? The derivative of the number times x, a slope times x, is just the slope. Okay, so that was our derivative. I'm going to simplify it. 12x plus 5. Okay, before we go, I'm just going to introduce one last concept. Okay, so all of these functions are some crazy curves. It turns out that when you have a curve and you want to know what the derivative is at a certain point, you do what we did in the investigation. Do you remember in the investigation? I had a curve, right? I had a curve. And we were finding out what the derivative was at certain points on the curve. And then there were these diagonal red lines which told us the derivative on the curve, right? And it varied because it's a curve, okay? So how do you find the derivative at certain points, right? Because like even if we have a derivative function like, I don't know, 12x cubed plus 7, that doesn't really tell you the derivative yet of any point. The way you find the derivative at a certain point is you plug in the x value. Do you notice how a lot of these derivatives have undefined x values? You plug in the x value. So if I want to know the derivative value at the middle of this parabola, I plug in x equals 0. If I want to know the derivative at this point, I plug in x equals 1. Do you get it? I just plug in x equals something into the derivative, and it'll give me a specific value of the slope at that point. That's why here it says, find the gradient of the tangent at the point where x equals 1, blah, blah, blah. We're going to plug in x equals 1. Okay? So what if we plugged in x equals 1 here? If we plugged in x equals 1 here, it would be 12 times 1 plus 5, which would be 12 plus 5, which is 17. So this derivative here, which is a function, it's got an x in it. We don't know what the value is. If we want to know at a specific point like x equals 1, then we just plug in x equals 1, and then it gives us a specific value. We can get specific values for the slopes at any point on the curve if we plug in the x position. That's it for today.